Hello everyone, welcome back to my channel, Predicting the Future. Today we're going to talk about programming. We're going to talk about R language specifically, and the subtopic we're going to talk about in R is the data type, vector, and matrices. So this is our first video about R, and I hope you guys will like it. So let's begin. So vector is very commonly used data type in R. It's it's a vector, so it's in mathematical way it's like a vector. So creating a vector is using a C function. I believe it's called column or something. So C and then the parameters, the values that uh, constructed the vector. Or the second way we can do is we can use columns to create vectors. So one column 5 is a vector of values 1, 2, 3, 4, 5. So the array, so assigning the vector to a variable, let's say x, is using an arrow and a bar, but we can also use the equal sign. Let's see, for example, y equal to c something, and the vector is it's a one-dimensional thing. So even though I have another x that is a vector, I create another vector y, which is c bracket x 0x. It's actually a one-dimensional vector, and that vector is 1, 2, 3, 4, 5, 0, and 1, 2, 3, 4, 5. Other ways of creating vector, like we can use sequence. So it's a sequence from 1 to 30. And the functions in R can be named function parameters. So let's, for example, the sequence function, we can have it has multiple parameters for this function, but we can specify what the parameter we're given to. Let's say to and from. We can switch the orders. It doesn't matter. We can give the name of that parameter and assign a value to that parameter. So that's creating a vector. Also, we can create vectors using a repeat function, the REP, and that's repeating the value of the first parameter multiple times. For example, x is a vector of 1, 2, 3, 4, 5, and then repeat. If we use repeat function of x, repeat that 5 times, then that will be repeating 1, 2, 3, 4, 5 times. So that's vector. Vector can also be used with other kind of mathematical operators, plus, minus, times, whatever, exponential functions, sine, cosine, mean, max, etc. So here is an example. Here there's a function called var is calculating the sample variance of a sample of vector x, the var x. So that's the variance of x. Or another very good example is the second example here, sum, which is creating, or well, the sum. This is the second example here is we are calculating the sample variance as well. By the formula, if you know the formula, you know it's x summation of x minus the mean square divided by n minus 1. So as you can see here, x is a vector, and we are summing over of a formula x here, but that's, the x has been used to be here is by element operations. So the first element of x will minus the mean of x squared divided by the length of x minus 1, and the second element plus, and then the sum will sum over all those iterations of x minus mean squared divided by n minus 1. And the third example here is here 1 over x, right? So x is a vector. What it outputs is 1 divided by each element of x, and that becomes a new vector. So in our example, that will be 1 over 1, 1 over 2, until 1 over 5. It's a new vector. It's very so we don't have to, it's not like traditional programming languages where we have to write a loop, and that expression here, I see here, the expressions of calculating sum using very intuitively of the formulas of mathematics, we can easily express what a mathematician wants to express and calculate the results that way. So here is another example here. So if we have different vectors, we can do any arithmetic calculations. And there's a way where, let's say we have an x and y, but they are different dimensions. X, let's say, is a vector of 5, y is a vector of 6, etc. And then we can plus 1, but 1 is just a scalar vector, a scalar number. So how does R handles that? So how R handles is that if let's say y is a vector of 11, size of 11, then but x is a vector of a size of 5. Then when we do that, x, it will be repeated. So it will be 1, 2, 3, 4, 5, and then so R will start from the beginning of reusing the values of x from the beginning. So that will be another 1, 2, 3, 4, 5, trying to catch up with the same size of the maximum size in this equation, which is y, which is 11. So that will be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then 1. That counts to 11. So that will be 2 times this vector, so 2 times each element of this vector x, and then plus y, and then plus a scalar. A scalar is the same, it will be repeated. 1 will be repeated 11 times, and that will be how this equation will be calculated. R is very powerful because it's very intuitive for mathematicians, similar to MATLAB and other programming languages in the scientific world. So, for example, here we can use complex numbers. Here we can do a square root of -1, which gives us the complex number I. So that's another example of arithmetic operations in R. So next thing is some special type of values in R. The first one I want to talk about is not available, which is NA. It's a placeholder for a space where we don't know the number yet. We just want to have a placeholder there, and then we can give a number later. So that's NA. So here is an example. We create a vector of 1, 2, 3, 1, 2, 3, and then the fourth number is not available. So it's a size, it's a dimension, it's a vector of dimension 4 with the last number of value not available. And to check, there's also a function called is.na is check if the vector if the value is not available. So if z, for example, z here is a vector, then what it gives us is another vector telling us each element, whether each element is not available or not. Same for, we can use double equal to do that. We can check z if equal to not available here. So next is not a number. Not a number is it's different than not available. Not a number is, for example, you're trying to divide by 0, or trying to do infinity minus infinity. Those the result of those is not a number. Another number is also true when we try to check test using is not available. So is not NA test of infinity minus infinity is also true. So same for 0 divided by 0 is also true. There's another function especially for not a number is is.nan. So it's checking whether it's not a number. Next is indexes. So a vector, so we know each element, we can go through each element. We can get every element by an index. Index start from 1 to the size of that vector. And so it's very, so let's say you see this second example, x plus 1. So what it does is it plus 1 of each element. It's element-wise operations. The first element plus 1, the second element plus 1, and so on until the end. We can also get a sub vector of this vector x. So we are taking a vector, a sub vector from 1 to 5. So we're only taking the first 5 elements. We can also do a sub vector from the end of this vector x. So here, on the left side, the last equation here, y equal to x bracket minus 1 column 5 is taken from the last 5 elements as a sub vector assigned to y. We can also create a sub vector using booleans. We can, for example, here on the right side, the first equation here, x exclamation mark a star nax, is to take all the values that has a value. It's not available. So that becomes we're taking all the elements, index elements of the vector x that is not an a, or is also not a number. Other examples, we can have pretty complex expressions trying to get a subset of this vector. So next example here, we have a pretty complex here, but if you see, we are checking whether we are getting the elements that is not available, and the value of the vector plus 1, the whole vector plus 1, that becomes a new vector, right? And then each element plus 1, and only if the element is greater than or equal to 0, then we take that value. So that's another example of creating a sub vector from a vector x. Vectors can also have names. So please look at the right side, the lower part of the right side. We create a vector called fruits. It's 5, 10, 1, and 20. And then we can assign names for each element in this vector fruit. The first element 5 is called orange, banana, a second is banana, a third apple, and last is peach. And that creates a named vector. So here, this name vector, that's what we just talked about. Name vectors assign each names. And the output you see here is orange corresponds to 5, banana corresponds to 10, and so on. And we can take out of some of the elements using, so let's say we create another vector lunch, which is taking fruit, but only taking those that has name apple and orange. So that gives us another sub vector, name vector, apple and orange. Next is we're going to talk about array and matrix. They're pretty much the same thing, but array is more powerful. Matrix is just a two-dimensional array. Array can be multi-dimensional, more than two-dimensional. So let's see how do we create a matrix here. On the left side, you see here we're creating an array of all the elements. The elements in this array, in this matrix, our matrix, is 1 to 20, and the dimension of this matrix is 4 times 5. So 4 rows, 5 columns. And you see here, the elements are being put column-wise. So 1 to 20 is put on the first column first, 1 to 4, and then second column 5 to 8, and so on. So it's column-wise. So think about that's the column space of the matrix, and the numbers were assigned column-wise. So yeah, so the right side is similar. So we create another matrix is 3 times 2 matrix, and the values of this matrix, the first column is 1, 2, 3, and the second column of this matrix is 3, 2, 1. So that's another example of using vector to create a matrix. And we can also so that's creating a matrix. So let's see here. So matrix, that's using array. We can also create a matrix using the matrix function. So matrix function is, if you look at the right side, the matrix function is another way of creating matrix. But as I said, array can be multidimensional. It could be two-dimensional, one-dimensional, or three-dimensional, whatever. So remember, the second parameter of the array function is dim, is the dimension. We give a dimension using C, which is the vector. C45 means it's a vector. It's a matrix of 4 times 5 vector matrix. If we do a multiple dimensional matrix, we can do a dimension equal to C456. So that's a 3-dimensional matrix, 4 times 5 times 6 matrix, right? But matrix function here, the matrix function here is only 2-dimensional. So you can only specify the elements of this matrix and the number of rows and number of columns. You can also use names, as we just saw earlier. So n row is the second is the name parameter, and column is the same as is also a name parameter. The last the fourth parameter, which is, see here, the true, on the right corner here, the last equation here, matrix 1 to 1, matrix of 1 to 6, number of rows 2, columns 3, number of columns 3, and last parameter true. The true here is to specify that the numbers I want to put into this matrix is now column wise. It becomes row wise. You see this output. We are now so the elements are putting row wise. So 1, 2, 3 horizontally, and then the next row 4, 5, 6. So it's not column wise anymore. So the last parameter is telling us, okay, I want to create this matrix using row wise order. So matrix also, we can get the dimension of the matrix using the dim function, which gives us a vector telling us the dimension of this matrix. We can also get the diagonal elements of the matrix using diag function, diag function. It gives us the diagonal elements of this matrix. So on the right side is what we just talked about. We can use array to create more than just 2-dimensional matrix. We can create 3-dimensional. So now we are creating a 3-dimensional matrix that is 2 times 2 times 2. And matrix is the same as columns. Remember when we try to do operation like mathematical equations where we have plus, minus, or times something, all the vectors together. If the vector size doesn't match, then the shorter vectors will be the missing elements on the shorter vectors will be filled up from the beginning of the same vector. So try to reuse the vector starting from the first element. So same for matrix. For example, on the left side, see we are trying to create a matrix of two rows, three columns. So we need 6 elements, but we only give them 4 elements: 1, 2, 3, 4. So it will try to reuse 1, 2, 3, 4. So that becomes 1, 2, 3, 4, 1, 2. So that's reusing elements. So matrix and array function both are the same, whether you use matrix or use array. If the elements you're given is less, then it will be reused if it's less than the dimension. Also, another way of creating a matrix is you can use two functions, which is one is cbind, which means column binding. Another function is called row bind, rbind, which means row binding. We're trying to bind multiple vectors into a matrix, right? So, for example, given the data x, y, x is a vector of 1, 2, 3, y is a vector of 4, 5, 6. Then if we do cbind of x and y, then create a matrix of 3 times 2. The x vector will be put on the first column, y vector put on the second column. Rbind is the other way. So the first vector x will be put on the first row, and the second vector y is put on the second row. It's the same for matrices as well. Suppose we have two matrices A and B, capital A and capital B. They are two matrices. If we do cbind, then the first matrix A will be put on the column-wise on the left side first, and then the second column, second vector matrix B on the right side of A. So that's 1, 2, 3, 4. That's A, and then 4 minus 3, 4, 3. That's B on the right side. Rbind is the same, but it's just row-wise. So A is put on first vertically on the first one, and the next one is B. And some basic matrix operations we can do with R. So A times B, that will be that can be calculated using A percentage sign and then a star, which is times, and then another percentage sign and B. So that's the normal matrix multiplication. And dot product or inner product, x inner product is y. We can use a function called cross prod of x, y. Also, the other way of doing dot product of vectors is the same as the matrix multiplication sign, the percentage star and percentage. So x dot product y can be written as x percentage star percentage y. And also, in dot product can be, as we know, that the dot product is the matrix multiplication, but it's that the first vector is a row vector, the second vector is a column vector. So the way we do the third way of doing dot product is we transpose the first vector. So we are transposing 1, 3, 4, 5. That becomes a row vector, and then times another vector, which is 1, 2, 3, 4, 5, 1, 2, 3, 4, but it's a column. So when we do that, that's dot product. So the second way of doing that is just x and y, exactly the same as without using transpose on the first vector. It's the same. So we don't, as you can see, by default, the percentage star percentage, when it sees its two vectors, it knows that what we're trying to do is dot product. If it's the other way, that we are not trying to do a dot product, then we specifically say, okay, the last vector y, we put it into a row vector. So we do a transpose on y, and that will produce a matrix. It's not on, so it will be a matrix. It's not a scalar. It's not a dot product anymore. Inverse, trying to find the inverse of vector A, then that we use a function called solve. We'll see why solve. But here is solve A means we're trying to get the inverse of A. Linear functions. B equals matrix A times vector X. If you try to solve this linear function, trying to get the value of X, that is same using solve function. Solve is matrix A, and then the second parameter is the output B, and that will give us the answer for X. So as you see here, the solve function not only for use for inverse, but also for mainly because that's used for solving linear equations. So the solve can be used either as inverse or solving a linear equation. The quadratic forms is similar. So X transpose capital matrix A times another vector X. The same. So it's as we know, so that we can write as X the R way of multiplication times A multiplication of X. That's how we calculate the quadratic value of that equation. If A is inverse, the way we'll do it is x times and then solve AB. Solve AB is just, that's how we find the solution of linear equation, right? So A inverse of x is just like solving a linear equation. So that's our basically suggests us to do that rather than using the quadratic way of doing that. Quadratic equation is when A is inverse because it's more efficient somehow. The conjugate transpose of A star, so that's conjugate function Co and J, and then T transpose, T is transpose, function T is the transpose function, and A, so that's the conjugate transpose. And matrix decomposition, so eigenvalues, eigenvectors is using the eigen function, eigen and A. It gives us two outputs. One is eigenvalue and the second is eigenvector. Determinant of A is the det and then A. That gives us determinant of A. Single value decomposition is using the function SVD to find the singular value decomposition of A. Give us three three outputs. One is the diagonal of the sigma, and then there's the matrix U and matrix V. QR decomposition is similar. It's just called QR. The function is called QR. Use QR and then give it the matrix A. It gives us the QR decomposition of matrix A. And that's it. I hope this basic introduction can give us you guys a little bit idea of the two of the important types in our language. And the next chapter, we're going to talk about other data types. That's also very important. And we'll see you guys next time. Bye.